Hello, good evening, my dear NEET warriors. Welcome to the Class 12 syllabus of your NEET 2026 preparation. Welcome all the droppers and the Class 12 students. And we are on to the next concept, the next topic of capacitors after completing successfully electrostatics and Gauss law. I hope you have watched it on your Vedantu NEET English channel. Yes or no? Do let me know quickly in the chat box. Very good. And keep that fire emoji, keep that thumbs up, and keep smashing that like button right away, right now, and keep answering all the questions. Okay. Good evening, all my lovely, dear future doctors. Nice to see all of you over here. So, we are going to talk about what is capacitors, what is capacitance, what are the different types of capacitors, and how do I get to those formulas, finding the force between the plates, field between the plates, and solving some amazing questions. This will lay a beautiful foundation for your next concept of combination of capacitors and all of that, right? So let's begin with the class. I hope you have smashed the like button. In case you have forgotten to subscribe, please do that right now. So let's begin with the class. So what is basically a capacitor? Let's try to understand it with a simple example. Imagine you have a conductor over here and you have another conductor over here. These are basically two conductors. These are basically two conductors. And what happens is these conductors, I connect it to a battery, to a battery. All right. So it is connected to a potential difference, to a potential difference basically. So battery creates potential difference, voltage across it. So what will happen as a result is that you will see that there will be some positive charges which will be stored on this conductor and an equal amount of negative charge stored on this particular conductor. So this potential difference, what it is trying to do, it is trying to suck out all those charges from one side and put it on the other side. So it's like saying I took the electrons from here and I put it over here. If an electron is going to move from here to here, a negative charge will come here, a deficiency meaning a positive will come on this side. So the voltage applied pulls the charges from one side and shifts it to the other side, thereby creating equal and opposite charges on those conductors. Now also notice, because of these charges present over here, there will also be some kind of an electric field which will be going from the positive to the negative side, from the positive to the negative side, like this. Yes, so from the positive to the negative side, this is how there will be an electric field between them. There will be an electric field between them. Now, till this point, everybody clear? And electric field always goes from high potential to low potential. Please remember that. Yeah, this side is at a higher potential. This conductor is at a higher potential. This is at a higher potential. And this is basically at a lower potential because it is connected to the negative terminal. Now you take those same conductors. Now you take those same conductors. You take those same conductors, and what you do now, maybe just connect a wire across it via some load, via maybe some device. It could be any device. Any device is generally called as a load. It could be a motor, it could be an actual resistor, it could be a some washing machine, it could be a fan, it could be a bulb. It is something, it has some resistance. What will happen the moment you take this, remove the battery and connect some kind of device, immediately you will start seeing that the charges will start flowing. The charges from here will start disappearing, and you will see that there will be a flow of charges. There will be a flow of charges. There will be a flow of charges through this. And whenever there is a flow of charges, that means there will be a current. But this current will only last for some time. because it is not continuously charged. There were some maybe 10, 20, 100 charges. All those charges will go on to the other side, and the current will flow for a small time. It will flow for a small time. It will flow for a small amount of time. And when will it stop flowing? Till it will reach an equilibrium. Basically, their potentials will become same. So eventually, so this will happen, okay, till till the potentials till the potentials become equal, till basically the potentials equalize, till the potentials equalize. So it will flow for a very small amount of time till the potentials equalize, and both the conductors will eventually become neutral. So you will see that eventually the conductors will become neutral. Eventually the conductors become become neutral in this process. They will lose out all the charge that they had accumulated. So when you connect a battery, the charges will move from one side to the other side, thereby creating potential difference and also electric field. And the moment you replace the battery with some device or some load, all the charges will move. Remember, conductors at different potentials, current flows until their potentials become equal. That is also a property of the conductor. So eventually they will flow out, and in this process they will lose out all the charges from one side to the other side, and it will become neutral. Essentially what happened is, this particular device was was having that capability of storing some kind of electrical energy in this electrical field. And this electrical energy was stored between these conductors. And I realized that energy, the moment I removed the battery and I connect a load, zoop, that current will flow. And for some time, there is some current which is passing, which is creating some heat, light, whatever effect that you want. So when I store this energy in the electric field between the conductors, I can use it for whatever application that I want. In fact, your mobile flash, which you have, exactly works through this principle. Yes, this flash, it comes for a small amount of time when you're taking a photo, and it goes off. And there is a sudden big burst of light. There is a capacitor. What happens is, before your camera is ready to turn on the flash, there is a capacitor inside which is storing a lot of charge and lot of energy in that conducting plates. The moment you press the selfie button or whatever, you are taking a photo, immediately what will happen? It is like, what will happen is that, okay, oh, yeah, what will happen is that all the charge will go in a small amount of time, thereby creating a sudden surge in the current or electrical energy, which is then converted into light. So wherever you need generally a sudden surge of current for a small time, there all you will use these capacitors. You might have also seen in some movies that some person is probably dying or maybe having some kind of an attack, and they take these two electrodes and they place it on the chest. Yes, the defibrillators which are called, right? They put it on the chest, and then they turn on that machine. The charge builds up, and sudden surge of charge will go, and some electrical impulses sometimes can probably make the person stable, or maybe suddenly can activate certain neurons and might bring that person back to life. Have you seen that kind of thing? Hi Tejas, welcome back. Yes, is it possible to come late? Means, Rama, the session is for around 1.5 hours to 2 hours. Hi, Dhananji, TS, everyone. Have you seen this kind of situation, guys? Everyone? Yes, very good. So, wherever you need some energy to be stored and also use that energy in a short burst of time, usually you will see the application of capacitors. So, basically, capacitor is nothing but an energy storing device. Capacitor is nothing but an energy storing device. And now we will see what is the capacitance also. So, a capacitor basically stores electrical energy between the charged conductors between the charged conductors in the electric field So that is what it can be said. What is a capacitor? This energy stored can be used to as a short burst of energy in short burst of energy. Example, a camera flash, right? So let me show you the demo of that right over here. Look at this. This is a battery. This is a conducting plate. This is also a conducting plate. This is a circuit. I have a switch here which I can move on to the other side. I can toggle it this side or this side. As you can see, this part of the circuit has an electrical bulb, something similar to the version of our camera flash. So let's say this particular battery, okay, I turn on that battery, meaning I am giving it some voltage. As you can see, there is some positive charge and some negative charge developed over here. I hope you are able to see this. Everyone with me? Yes? Hi. Mugilan, welcome. Good evening. Yes, Bhargav? Okay, perfect. If I remove the voltage difference, the charge will also go away. As I increase the charge, I will have to apply more voltage onto it. Okay. Now what I will do, I will move the switch to the neutral position. Do you see the charges have nowhere to go? They cannot escape. So the charge is still there on the plates or on the conducting material. This has positive, this has negative. It's trapped now. There is definitely some electric field over here. I can show that electric field like this. I hope you are able to see it. Absolutely clear? Everyone, can you see those black lines? Those are nothing but electrical fields. Okay. Now that electrical field has stored a lot of energy, and you can see I can change that field by lowering the voltage. So if I lower the voltage, charge will reduce. And if I increase the voltage, the field, the charge, everything will keep on increasing. Okay, so right now the energy is trapped. As soon as I move this switch to this particular point, this circuit will get completed. All these charges will move and they will try to neutralize the charge on the other side. And as a result, there will be a short duration of current which will lighten up this bulb. Observe carefully. Oh my God, look at this bulb. Zoom. And yes, the current faded away. The current just died. There was too much brightness. It was like blinding the eye. Why can't I connect the battery directly to the bulb? Yes, you can, but then the brightness will not be that much. But when I store the energy and give it suddenly, then there is a sudden boost of energy. So let's try it again, but not with so much current, not with so much charge, little bit less amount of charge. Okay, little bit less amount of charge. So got it to neutral, the charges can't escape. Let me cut here. The brightness is there, the flash is there, but not as bright as when it was like this. When I charge it completely, observe, I move it. Oh my God, look at the brightness. It was amazing to see it. That's it. The current has died off. All the energy got utilized. So this is exactly what a capacitor does. How many of you are now able to visualize what is a capacitor, what it does, and how it behaves exactly? So what is the symbol of a capacitor? By the way, the symbol of a capacitor is like this. You show two conducting plates, and these are the two terminals of a capacitor. So that's the simple symbol, and the capacitance is C. Okay, so how do I define capacitance? Observe carefully. One side will have a positive charge, one side will have a positive charge, the other side will have a negative charge, and there will be some kind of a voltage difference across the plates. So this is the potential difference. This is the potential difference potential difference. Q happens to be the charge on the capacitor, the charge on the capacitor. Somebody might argue, sir, there is positive and negative, so won't the total charge be zero? 100% correct. The total charge is zero, but when somebody asks you what is the charge on a capacitor, then it is always zero, then there is no point of talking about it. We are talking about specifically any one charge has magnitude. So any one of those charges magnitude is what is referred to as the charge on the capacitor. But if somebody asks you what is the net charge, the net charge obviously will be Q plus the negative Q, which will always be zero. But that is not what we refer to when we ask what is the charge on the capacitor. We are not talking about net charge. We are mentioning basically any one of those charges magnitude. So it so happens that this particular charge is found out to be directly proportional to the potential difference which you apply, and that constant of proportionality is then called as the capacitance. So Q is equal to capacitance times of voltage. So this C over here stands for capacitance. It stands for capacitance. Now we can easily find out the unit of capacitance. So the unit of capacitance, think about it, it will be nothing but the unit of charge, the whole thing divided by the unit of the voltage. So what is the unit of charge? Charge is nothing but coulomb. And voltage is nothing but in volts. So coulomb per volt is nothing but the unit of capacitance, but that is given a name that is called as a farad. It is called as a farad. So 1 farad is when you are able to store 1 coulomb of charge when you apply 1 volt. Keep this in mind. Okay, very, very crucial definition. So this is the SI unit, okay, coulomb per volt, which is a farad, and this is the formula. Q is equal to C into V. Also notice that this particular capacitance, it mainly depends on the geometry. That means what is the length of the plate, what is the size of the plate, what is the shape of the plate also, and also what is filled inside. So the material filled inside, the material which is filled inside or between the plates of the capacitor, material which is filled inside that conductors. So that is what the capacitance depends on. I have seen a lot of students make this mistake, and this is very, very common. I have asked many students, what happens if voltage increases? Will the capacitance increase or decrease? A lot of students tell me, sir, if voltage increases, capacitance will decrease so that the product will remain constant. Then I ask them one thing, why should that happen? I mean, what is the need for the charge to be constant? Is there some rule? The charge can increase. So if the voltage increases, technically the charge increases. It's also the other way around. If voltage decreases, the charge decreases. Capacitance does not change. It is not dependent on the charge or voltage as such. So it is dependent on the charge by voltage ratio. So this particular capacitance only depends on the shape, geometry, etc. So once you have a capacitor, it is a fixed thing. So depending on how much voltage you apply, automatically that much charge will be developed, but you cannot change capacitance by changing voltages. Keep that in mind. And as you can see over here, as I increase the voltage, the charge increases. So charge is proportional to the voltage. As you can see over here. Is that absolutely clear, my dear warriors? Everyone? Yeah? Okay. DDLC, you can put those comments in the comment section after the video is over. All right. Okay. Right. Okay. What's the difference between a capacitor and a battery? Very good question, Amina. See, a capacitor basically has the energy stored in the form of electrical energy. but battery stores it in chemical form. Number two, battery will always supply constant voltage, but capacitor gives that voltage in a sudden burst. Battery will last longer, capacitor will not last long, it will last for few milliseconds. Zip, it will give that power and it will die out. Okay, so these are the main differences. First thing, the type of energy. In capacitor it is electrical, battery it is chemical. Second thing, battery lasts for long, capacitor hardly few moments. Battery gives continuous voltage, constant voltage. Capacitor, the voltage is very high initially, then it suddenly dies out as it supplies the energy. Okay, that is the main differences. I hope this is absolutely clear. Okay. Yes, Kavin, that is more than enough. Why not? Yeah, 7 months is more than enough. Okay. All right. Moving on. Moving on now to the next thing over here. When we give a capacitor some charge, this is one of the most important question. Many people I have seen, they do not know this. Where do you think the charges are exactly? Because I just tell that the charge is Q over here and minus Q over here. So what exactly does happen? Is it like Q by 2, Q by 2, this part has Q by 2, this part has Q by 2, this part has minus Q by 2, and this part has minus Q by 2? Or this is option A. Option B, this part has 0, this has Q, this has minus Q, this has 0. Or option C, this has Q, this has 0, this has 0, and this has minus Q. Or option D, none of the above. None of the above. What do you think is the right answer for this? What kind of configuration will you get if this plate has positive Q, this plate has negative Q charge? Which of the configurations should you get? Come on, everybody spam the answer in the chat box, A, B, C or D. Everybody, come on, think about it. I have taught you how plates work when charged in this particular lecture. Conductors, dielectrics, plate, shells, sphere problems. If you have attended that class, this shouldn't be such a big issue at all. See guys, if you take this particular plate over here and this another plate over here, and I tell you, listen, the total charge on this plate is positive Q, this plate is minus Q. I have told you this before. To figure out the distribution of the charges, first figure out what is the total charge. And the total charge over here is positive Q plus negative Q. So it will be basically 0. So when you divide 0 into two parts, it will still be 0 and 0. So whatever those equal parts are, that is always on the outermost plates, always on the outermost surfaces of the plates. So now the inner plate will have, by charge conservation, naturally plus Q, so that their sum is positive Q. Here it should be minus Q. Okay, so this is how the configuration is: 0 plus Q minus Q and 0. That means the correct answer for this particular question is obviously this one, option B. So option B is the right answer. Option B is basically the right answer. This is absolutely clear, my dear warriors. Very good, Muglian. Yes, Tejas, perfecto. Awesome. Let's solve some questions coming up on your screen. A capacitor is connected to a battery so that a charge of negative minus 100 plus 100 is obtained. The capacitance is how much? Okay, so we need to figure out the capacitance. We know Q is equal to C into V. So capacitance is charge by voltage. The charge, take any one of the charges magnitude only, which is 100 microcoulomb. Okay, and divided by the voltage, which is basically 20. 0, 0 cancels, 10 by 2 is 5, so it will be 5 micro. But remember that capacitance is always in farad, so 5 microfarad is the answer. So 5 microfarad, which is option B. Remember, the capacitors which you usually get in the market are usually in microfarads or picofarads. Millifarad is a huge capacitor and a farad is very huge unit. So normal capacitors are very, very small. If you're wondering how capacitors look like, you should probably just Google it out. How capacitors look like. Capacitor, yeah, oops, not capacitor head, just capacitor. So this is how capacitors basically look like. You can see that they are barely the size of your finger or your nail. So this is how the capacitors look like in the market. Okay, so these are the examples of capacitors. So this is a very huge capacitor, very big. Usually they are very teeny beeny bits, right? So that's a capacitor. Moving on to the next one on your screen. Wow, this is a JEE mains question. Which one of the following is the correct dimensional formula of the capacitance in farad? MLTC stands for mass, length, time, and charge. Okay, let's start with it. We know that Q is equal to capacitance into voltage. Therefore, capacitance will be nothing but the charge divided by the voltage. Okay, but if you talk dimensionally, dimensions of capacitance will be the dimension of charge. Dimension of basically Q is nothing but charge and voltage over here and voltage over here. Voltage, we know the definition. It is the work done per unit charge. So it is nothing but the dimensions of work divided by the dimensions of the charge. So what I get now is that charge goes on the top. So it will be basically the dimension of charge, the whole square, divided by the dimension of work. Oh, perfect. So therefore, the dimensions of capacitance will be dimension of charge. What is it given? For charge, they are using the symbol C. So it is C and this raised to 2. And dimension of work, we know this as a standard. It is mass, length raised to 2, T raised to minus 2. Bring this on the top. So this will become M raised to minus 1, L raised to minus 2, T raised to 2, C raised to 2. That is the final answer. M raised to minus 1, C raised to 2, right? And L raised to minus 2, T raised to 2, which is option C, right over here. C for your Captain Shreyas, right? Very good. Excellent. All right. Okay, Manda, Shreyan, definitely noted. And please leave that as a comment, guys, because what happens, so many things you guys keep telling, talking. Also put it on the chats. Also, it helps other students to think of some more ideas, and also put it in the comments. See, I always read your comments. Yeah. So whatever comments, even new videos, old videos, I keep checking. It's not like Shreyas Sir just takes class and oh, I chill out and I sleep. No, I keep reading, I keep replying whatever I can, but I get thousands of, things here and there, like on the Telegram, on WhatsApp, on Instagram and YouTube. But I keep a track as much as possible and try to respond or at least make videos based on your comments or see what we can do. Okay, so please always put down those comments. It is very essential. And yes, please like the video also. People forget. Okay, we take so much of effort for you. At least we deserve a like, which costs nothing for you. Cool? Okay. This particular capacitor is charged at a rate of these many coulombs per second. How long will it take to raise the potential difference between the plates to reach 10 volts? So this capacitor will slowly keep increasing their charges and eventually reach 10 volts. So when it reaches 10 volts, how much charge will it have? So at 10 volts, let's say the charge on it is basically Q. So this particular Q is capacitance multiplied by voltage. Capacitance is 500 micro and voltage is basically 10. So this is nothing but 5000 micro. 5000 micro, but this is in coulomb. So this is the total charge. But we have been given it is charged at 100 micro coulomb per second. So any kind of rate of charging is basically how much charge are you putting per unit time. So that rate of charging is given to be 100 micro coulomb per second. The total charge that I want is 5000 micro coulomb. Time I do not know. So therefore time will be nothing but 5000 divided by 100. Two zeros cancel. So I will be left with 50, but that 50 is obviously in seconds. So the correct answer is C option, which is Captain Shreyas, 50 seconds. Perfect. Cool. This is how you can solve these standard questions. Now let's talk about the different makes, the geometries of capacitors which we usually deal with in JEE Physics. Okay. So what type of capacitors we have? In NCERT, if you see, mainly they will talk about parallel plate, but we might have to push the lecture a little bit higher, guys, for cylindrical and spherical type. Only then it, makes sense, right? Because for JEE Advanced and maybe some exams, they have these capacitors too. So there are three varieties of capacitors which we study. The most detailed study you will do it for parallel plate. Cylindrical, not so much, not so important. Spherical, maybe only sometimes they might ask, that too very rare, and some specific category of questions. The most important being the common type which is used, which is parallel plate capacitor. Just like the name suggests, it's nothing but two plates which are parallel placed in front of each other. So think of it like this. Okay, let me use Tattva books as parallel plate capacitor. It's just like two plates over here in front of each other. That's it. So this is a parallel plate capacitor. One plate positive, one plate negative. This plate higher potential, this plate lower potential. So there will be electric field in between them, just like over here. The distance between the plates is small d. The area of this plate, so the area of this plate is basically A. Is that clear? So that is how the nomenclature goes. So let us start putting things down over here. Okay, parallel plate capacitor, nothing but A is area of the plates, D is basically the distance between the plates, and Q is the charge, and we want to figure out what kind of capacitance will this store. Okay, we want to figure out what is the capacitance of this particular parallel plate capacitor. So our aim is to find its capacitance. Okay, I will keep one thing in the back of my mind. Somehow if I show charge is something into voltage, whatever that something is, that something will be the capacitance. Agree or disagree? Somehow if I'm able to show charge is proportional to voltage, that constant of proportionality will become the capacitance. Okay, fine, sir. So somehow you are going to show charge is proportional to voltage, huh? Yes, but how do I do that? That is the problem. There is some kind of electric field between the plates of the capacitor, as we can see over here. Maybe somehow field voltage we can relate. Maybe then I will get it. Yes, sir. Definitely. Why not? So one thing I can do, okay, this particular positive charge right over here, this particular positive charge over here will give rise to electric field here like this and like this. Oops. And like this. Remember, any charged sheet will give electric field on both the sides. How much will that field be? It will be sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Same way, I can also argue this negative charges over here will give rise to electric fields like this. Because it is negative, it will be attractive in nature. So it will give rise to electric fields like this and like this. Now please note that this electric field line will continue its journey like this. And also please note that this electric field line is coming right from here. Okay, it is coming right from here like this. It will go like this onto the negative plate of that other side. Interesting thing to note is that even this magnitude of the electric field will be sigma by 2 epsilon naught. Sigma by 2 epsilon naught, sigma being the charge density. Charge density is the same magnitude wise. Notice what is happening. On this side, this field is this way, this field is the other way. So they are cancelling out each other. Here also, this field is here, this field is here. So it is cancelling out each other. But over here, these two fields are in the same direction. So they are basically adding up. That means outside the capacitor, electric field outside the capacitor is 0. Electric field outside the capacitor is 0. Are you getting me, my dear warriors? Why the electric field is 0? Kevin, we'll understand that when we study AC circuits. We have not yet reached that chapter. Okay? Right. Okay. Here they are adding. So there is definitely electric field within the plates of the capacitor. How much will that be? That particular electric field will be nothing but the sigma by 2 epsilon from one side and also the sigma by 2 epsilon from the other side. So both of them will add and we will get sigma by epsilon. What is sigma, my dear warriors? What is sigma? Sigma is also our batch name. Yes, sigma is charge per unit area. How much charge? Q, area A. So Q A by epsilon naught. Sorry, Q by A epsilon naught is our sorry guys, I think there was a small issue. The internet just got disconnected. I'm back. Okay, let's continue. So I just said that the net electric field is Q by A epsilon naught. Okay. Now, how do I use this electric field in our derivation? So let's talk about that. See guys, the electric field is also given by a formula called negative dV by dr. But if I'm only interested in the magnitude and I know that this particular electric field is constant, so I can also say it is nothing but the total potential difference upon the distance. Upon the distance. So what is the potential difference between this plate and this plate? It is obviously V volts. So this and this point, the voltage difference is basically V volts. And what is the distance between these 2 points? It is nothing but D. So it is V by D. And this electric field magnitude, we just got it over here. So this was the net magnitude of the field, whatever we have got. So this magnitude is Q by A epsilon naught. So this is Q divided by A epsilon naught. So I have an idea now. How about writing this as Q is equal to, observe this carefully, V is as it is. On the top, A will go, epsilon naught will also go, D will stay below as it is. Compare this with, compare this with, compare this with, compare this with charge is capacitance multiplied by voltage. Immediately you have your answer, and the answer is that the capacitance is nothing but epsilon naught A by D. It is epsilon naught A divided by D. So this is the formula for the capacitance of a parallel plate capacitor. Like I said before, when I told you about capacitance and we defined it, there only I told you clearly it depends on the shape, geometry, etc. So definitely everything makes sense now. It is not dependent on the external voltage or the charge. It depends on the size, the geometry, etc. If the material inside changes, permittivity will change. Epsilon naught will become epsilon naught into K. So if this particular capacitor has some medium present inside, so I can just mention over here, if some dielectric medium, if some dielectric medium is present is present inside, then the new capacitance, will be epsilon naught into K. That's it. That's the only difference divided by D. This K is the dielectric constant of that particular medium, right? K is basically dielectric constant of that medium. You can also write that the new capacitance is epsilon of the medium into A divided by D. So instead of permittivity of vacuum, you have permittivity of the medium, which is epsilon naught into K, Is that absolutely clear, my dear students? Everybody with me? Yeah. Yes. Yes, Fatchis, I'm covering all the concepts of capacitors, man. Yeah. Sir, is your brother on the another live on this channel? No, that is a loop video. That is because we have a final call going on for the Sigma batch. So it's not my brother. It's me only. Just it's a pre-recorded version, which we are just playing it as an announcement for all the students who want or might miss the, Sigma batch entry, right? Because that is the final entry. Okay. Fair enough, sir. I understood now. Okay. So now that we have it, okay, let's see whether you are able to solve this question. A capacity of a parallel plate capacitor is 10 microfarad when the distance is 8 centimeter. If the distance between the plates is reduced to 4 centimeter, then the capacity will become how much? As you can notice in this particular problem, the distance between the plates is reduced to 4 centimeter. Earlier it was 8 centimeter. Rest everything is a constant. So we know that capacitance, if it is epsilon naught A by D, therefore capacitance is inversely proportional to D. So therefore, can I say C2 by C1 is nothing but D1 by D2. So what is the new capacitance? I don't know. What is the old capacitance? It is 10 microfarad. Okay. What is original distance D1? It is 8 centimeters. What is the new distance? It is 4. Sir, shouldn't I convert centimeters to meters? Well, even if you do, how does it matter? I mean, there is centimeters on the top, centimeters below. Anyways, it will cancel. So don't worry. Sir, here this is in microfarad. So should I convert? Don't worry. The answer I will get over here is also for microfarads only. So therefore, C2 will be 8 by 4 is 2 and this 10 will go on the top. So therefore, the new capacitance will be 20. Yes, but this 20 will be in microfarads. This 20 will be in microfarads, which is C option. Is this absolutely clear, my dear warriors? Yeah, right. Great. Now, also one important thing is that this side is positively charged of the parallel plate capacitor, the other side is negatively charged. What do positives and negatives do to each other? That is the basics of electrostatics. Yeah. What is the basics, guys? Obviously, the positive will attract the negative. The positive will attract the negative. So, won't these plates will always be in a tendency to just like like stick to each other like magnets? Why not? Of course. So there is a force between the plates of a capacitor, so you need to prevent them from flying off and sticking to each other. It's like one Pandu and Champa, they love each other and they are being held back by someone. Hey, you cannot meet Pandu. Hey, you cannot meet Champa. So there is some force of attraction pulling them together for the sake of their love, but you're holding them back by applying an equal and opposite force. So how much is that force is what I'm interested in. So a very interesting thing now, the field between the plates of a capacitor, we just calculated, we just derived it, and we saw that it is Q by A epsilon naught. And through this field, I can find the force. So the field between the plates, the plates, field between the plates is nothing but Q divided by A epsilon naught. So then one can argue that the force F is nothing but the charge multiplied by the field. So It is the charge multiplied by the field. This plate has charge Q, this plate has minus Q charge. I am interested in the magnitude of the force, so I'll just put Q. I'm not interested in the actual sign. I know that, yes, the sign will just change the direction, that's all. So charge is Q, field is nothing but Q by A epsilon naught. Okay, then the answer which will come out will be Q square by A epsilon. But let me tell you, that answer is wrong. There is something wrong in this derivation. Can you point out to me what is the wrong thing? What is that mistake which I have done in this derivation to figure out the force between the plates of a capacitor? Just think about it. Just think about it. The very big conceptual blunder. And to give you guys that hint, let me tell you that imagine there is some positive charge here, okay, and there is some negative charge here. This positive charge, let's say, is giving some kind of electric field like this, some kind of electric field like this. Then the force on this negative charge, then the force on this negative charge will be the charge multiplied by this particular field. But this field E which is there, this field is because of whom? Positive or negative? This electric field is due to due to the positive Q charge. It's not the net electric field. In fact, if I had this positive charge and if I had this negative charge, and I tell you, hey, listen, they together have some net electric field, this net electric field can't be used to calculate the force on them, because this net field can be used to figure out, if I place some other charge here, then how much force will that experience? That force will be nothing but that particular Q multiplied by this particular field. This particular field. This is the answer when the field over here, this is basically the net field due to both of them. This field incorporates this guy's contribution and the negative charge's contribution. How can the field due to a charge apply a force on itself? It's like saying, sir, I have a charge here and it is generating a field, sir, like this. And sir, because of this field, there is a force on the charge. No, 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 no. This field will apply a force on some other charge. This field is due to this charge. It can't apply a force on itself. So be aware of it. So guys, this net field can't apply force on any of these charges, but on a third charge, that becomes external for that and it can apply a force. So when you use field due to a single charge, that's when you can find the force on the other charge. So guys, over here, this calculation is 100% wrong. This calculation is 100% wrong. So in fact, I can use this calculation for calculating something else. Force on a charge placed in between. Charge placed in between the plates. In between the plates. And this is the field between the plates. But this is not any field. This is the net field. This is the net electric field between the plates. So it is due to both positive and the negative. So if at all I am having some kind of a charge over here, Q, and obviously there is this electric field which is going, so that charge will now experience a force like this, and that force will be nothing but this particular charge multiplied by the field. So that force magnitude, so that the force magnitude will be nothing but QQ by A epsilon naught. QQ by A epsilon naught. This is a very, very important result. Okay, this is a very, very important result. Is this absolutely clear? Okay, everyone? Okay. I think unknown, I just explained it. What is the difference between capacitors and batteries? Somebody had just asked it just few minutes back only. Okay, I think I have just explained it, but just to repeat, capacitors store electrical energy, batteries store chemical energy. Capacitors give the energy stored in it very suddenly. Batteries give it smoothly over a long period of time. Okay, second and thirdly, capacitors, the voltage varies with time, but batteries, the voltage, they maintain a potential difference as long as you have those electrolytes in that. Okay, perfect. So if one were to calculate the force between the plates of a capacitor, then what I need is not any random electric field, but rather I need the electric field due to any of these plates. The electric field due to any of these plates. So the field due to any one charge plate, due to any one of the charge plate, if that is basically E1, that particular E1 will be exactly half of this previous electric field, which is basically half of that net electric field which is there, the net electric field which is there. So hence it will be nothing but Q by 2A epsilon naught, that is electric field due to any one of those plates. Therefore, if I want to find out what force will be applied, so the force on the other plate, F will be nothing but, you can take that particular charge, maybe it is Q in magnitude, I'm just interested in the magnitude. It is nothing but the charge multiplied by the field. Charged multiplied by the field. That field is nothing but Q by 2A epsilon naught. The charge is again going to be Q. So therefore, my force will be Q square by 2A epsilon naught. That number 2 will come over here. That is the major change. Q square by 2A epsilon naught. Okay, Q square by 2A epsilon naught. But force on a third charge will be QQ by A epsilon naught. There is no Q square, it's QQ, and there is no 2 over here. But when it comes to the force between the plates, there is that number 2 and there is that square also over there. That's one big dramatic difference which every student can misunderstand. Let's go now to the questions. Here comes the first question on your screen. The force between the plates of a parallel plate capacitor, capacitance C, distance D, voltage V is how much? Okay. Yes. Book, I'm not in the pro batch, I'm in the Sigma batch, but you will find teachers like me or better than me only in the pro batch. Okay. So we can't have all teachers everywhere. Then if that pro teacher is teaching on YouTube, you'll ask the same question to that pro teacher. Sir, are you in the pro batch? So teachers are just like me because the hiring process is the same. The level of the teachers is the same. We are all NITians, IITians. We are all experienced. It's not like, one teacher is this, one teacher is that. Almost all teachers are equivalent in Vedantu. That's what you will see, right? Okay. Gauss law flux is already done. Already done. Yes, separate classes. Already done. Yeah. Is charge a form of energy? No, it is not a form of energy. And yeah, charge is just an intrinsic property. Like mass is not energy. Mass is just the property of matter. Yeah. So same way, charge can create the energy around it with another charge, but charge is just a property of material. Okay. So in order to figure out that particular force, use the formula, which is Q square by 2A epsilon naught. But I don't see area, I don't see charge also. So what do I do then? Well, capacitance and charge are related to each other. Q is nothing but C into V. So it is C into V whole square by 2A epsilon naught. Why did I do that? Because I can now get voltage in the answer maybe and then probably solve the question. So we now have C square V square by 2A epsilon naught. but I don't see A epsilon naught anywhere. So I have an idea. Guys, capacitance was epsilon naught A by D. So why not write epsilon naught A as C into D? C into D is epsilon naught A. So why not replace that over here? So therefore, you will get C square V square by 2. And over here, we can just write it as C multiplied by D. A C and C will get cancelled out. Therefore, I will get the force as C will be remaining, V square is there, and 2 into D will be there. CV square by 2D, which is option number A, of course. Got it? So just had to manipulate it. Charge was C into V. That is the first formula which we have used. So Q over here is capacitance into voltage. The next thing that we used is epsilon naught A. I converted into C into D, and replacing that CC cancelled, and we got option A. Yes, very good, Spidey. Very good, Rama. Moving on now to the other 2-3 types of capacitors which are still remaining. Let's do that. Yep. 12 JE chapters. Okay, fine fetches. I'll definitely think about it. The PYQ series basically you're talking about. We'll do that, but not now, but in due course of time. Okay, now is not the time. Now is the time to complete the theory part, but we'll get that also. Cylindrical type of capacitor. The derivation is very much similar. Somehow show the charge is proportional to the voltage. And the main point is that the cylindrical capacitance comes out as follows. A cylindrical capacitor is made of two concentric cylinders. So basically you have nothing but two concentric cylinders, of radii A and B. Also height, let's say height is L or H, whatever you want to call it. And there is field between them. Electric field outside is always going to be 0. And one of the cylinders is positive, one of the cylinders is negatively charged. So you will get that the capacitance is 2 pi epsilon naught L, and here you will have log of B by A. This is the formula that you get. This is the capacitance of a cylindrical plate capacitor. 2 pi epsilon naught into height of the cylinder divided by log to the base E, which is ln B by A, bigger radius by the smaller radius. This is the formula for a cylindrical plate capacitor. Just to give you example on that, I think we have a question like this. What is the capacitance of a cylindrical capacitor of height 10 centimeters having inner radius 2 millimeters, outer radius 4 millimeters? So as you can see very well over here, this is outer radius. So let's say the bigger one is B, the smaller one is A. The height is already given. This is basically L. So we want to figure out the capacitance. So let's start by writing down the formula. 2 pi epsilon naught multiplied by L divided by log B by A. Now, one special thing about 2 pi epsilon naught is I can write this as 4 pi epsilon naught by 2. Keep it aside. This L is there and log of B by A is there. This 4 pi epsilon naught is nothing but 1 by K, which is Coulomb constant. So this is 1 by K, and that number 2 is there anyways, and this L by log of B by A is also there. This is nothing but your Coulomb constant. If you remember, Coulomb constant was 1 by 4 pi epsilon naught. So 4 pi epsilon will be 1 by K. That is the trick that I have pulled up my sleeve. Okay, sir. So what is the capacitance? Tell me. So 1 by K means 1 by 9 into 10 to the power 9, which will make our calculations easy, into 1 by 2 multiplied by the length. Length of the capacitor is basically 10 units divided by log of B by A, that means 4 millimeters by 2 millimeters. Anyways, it is millimeters. So that millimeters should anyways get cancelled. So don't bother converting it into meters. Okay. So this will become this 10 will cancel. 9 twos are basically 18, and this will be 10 to the power 8, and this will be 1 divided by log of 4 by 2 is 2. So this will be nothing but 10 to the power minus 8 divided by 18 log 2. If you want, you can put the value of log 2 and substitute and get in decimal places. But yeah, this is the simplest way. Before substituting, the answer will be, okay, this answer of course will be in farads. This will be in farads. Is this clear? How to find the cylindrical capacitance? Okay, so this trick helps you simplify it. Otherwise, you will have to multiply with pi, again an irrational number, and 8.85 10 to the power minus 12 becomes tedious. Why do all that? This is a simpler way of calculating. Okay, sir. So that is cylindrical capacitor. The last type is the spherical type of capacitor. So for a spherical type of capacitor, you have two concentric spheres. Again, you have two concentric spheres of radii A and B, which are charged, and because of that, there is a field inside. Remember, again, the electric field outside will be obviously 0. Using the same technology, using the same derivation method, somehow show charge is proportional to the voltage, and that constant of proportionality basically becomes your, capacitance. You get the capacitance value as 4 pi epsilon naught, whole thing divided by 1 by A minus 1 by B. That's the difference. Here you will get 4 pi epsilon. For parallel plate, it was just epsilon. For cylindrical, it was 2 pi epsilon. So 4 pi epsilon, 1 by A minus 1 by B. Also keep in mind that if the concentric spheres, if the space between them is filled with some medium, dielectric medium, the only difference will be there will be a dielectric constant K over here. That's it. Okay, not the Coulomb constant, dielectric constant, because permittivity of vacuum will be replaced by permittivity of the medium. That's it. That's the only difference. Otherwise, the rest of the formula will be the same. Okay, ln is the log to the base E, amina. Okay, right. Where two discs attached to the rod and rotate about the axis. So that's nice. We'll be solving, guys. User phone as a J advanced question. Current electricity very soon. Yes. How 1 by A, 1 by B came? That comes because of integration and all of that. Basically, if you had to look into it, it comes like this. You have to say, for example, this is our positive charge and it is creating an electric field like this, right? And if you are at any distance, let's say R, at this point, that particular electric field will be Coulomb constant, which is 1 by 4 pi epsilon naught, the whole charge Q divided by R square. This is field outside a shell. Right? This formula we have seen it before. Now use this method that since E is minus dV by dr, therefore dV is nothing but minus E dr. So then integrate this. Integral dV is minus integral E dr, and that's how you will get it. So you'll have to put over here integration of dV is basically the total voltage difference. Okay, so we are going from high to low. So let's say this is V plus to V minus. So it will be V minus minus V plus, and this electric field from here, which is 1 by 4 pi epsilon naught and what is this? Q divided by R square, and this is basically dr. So integrated with proper limits, you are starting from radius A to radius B. Yeah, so radius A to radius B. So integrated, and then solving this, you will somehow get that the voltage is or voltage over here is something into the charge, and that something over here, if you shift it on this side, you will get capacitance because Q will be equal to CV. So this is how you get it. So over here, you will most likely get, 1 by A minus 1 by B divided by 4 pi epsilon naught. This is what you will get. So after solving this. So Q is equal to C into B. So C is 4 pi epsilon naught 1 by A minus 1 by B after integration. Is this clear? That is how you get it. Yeah? Clear? Okay. Now, this is a spherical type of capacitor. Spherical type of capacitor, we can just see a question on it. In a spherical capacitor, if the radius of outer sphere is R, the difference in the radii of outer and inner sphere is X, the capacity is proportional to. I think direct formula question. The outer sphere radius is R, that means B is basically R. The difference in the outer and inner sphere, that means B minus A is basically X. But wait a minute, B is R, so R minus A is equal to X. Therefore, what is it? A will be nothing but R minus X. So we have now technically got the value of A also. We also got the value of B. So now we can find out the capacitance. Capacitance is 4 pi epsilon naught 1 by A minus 1 by B. So 4 pi epsilon naught 1 by A means 1 by R minus X minus 1 by B. B is nothing but R. So therefore, capacitance will be 4 pi epsilon naught. Here take the LCM. So it will be R into R minus X. Then over here we'll have R and minus of R minus X. So this will be 4 pi epsilon naught. R will cancel, minus minus will become plus. So X divided by R into R minus X. So this will be 4 pi epsilon naught. R into R minus X will go on the top, the whole thing divided by X. So what is the capacitance proportional to? R into R minus X by X. R into R minus X by X, which is option D. Yeah, so you can see it very clearly over here. R into R minus X, the whole thing divided by X. That is what the capacitance is proportional to. Is this clear? Very nice question. Now, there is a special consideration of spherical type where the outer sphere does not exist. Only one shell is there. That is called as isolated spherical capacitor, where you have a single conducting sphere which is charged. One might then think, where is the outer shell? Well, you can think as if the outer shell is at infinity, because the electric field lines which come out from this kind of a shell, I hope you were able to see this, the electric field lines which come from this particular shell, they are eventually reaching infinity. That means they are never ending. So this is infinity, as if the other plate is at infinity. Oh, so if this isolated sphere has a radius of r, then can I easily argue that therefore the inner radius is r and the outer radius is basically infinity. The outer radius is basically infinity or tending towards infinity. So B, can I just say it is not equal to, we cannot have any number equal to infinity, so tending towards infinity. So if I use by derivation for spherical type, which is 4 pi epsilon naught 1 by a minus 1 by b. This will become 4 pi epsilon naught 1 by radius minus 1 by infinity. What is 1 by infinity? 1 by a very large number is 0. So this will just become 4 pi epsilon naught 1 by r. R goes on the top, so it will just become 4 pi epsilon naught multiplied by r. So that is the capacitance of an isolated sphere. A single isolated sphere, it is 4 pi epsilon naught into r. Simple. What a nice thing. So a single charge sphere is also a capacitor. Let's solve a question on that. Oh, an isolated spherical drop is there and it has a charge Q. It is broken down into 27 drops. Find the new charge on each drop. New potential is to old potential ratio. New is to old capacitance ratio. Okay, let's try to figure this bit out. See, we have capacitor which, let's say, has some radius r. It had some charge on it. It had some charge on it, and the charge was plus q. You now broke it down into small spheres like this. Each sphere will have a new radius, some new charge, like that. 27 drops or 27 small spheres. That is what you have converted this into. Okay, fair enough. In this process, what will happen? Obviously, if you break it into 27 drops, each drop will have the original charge, whatever is that initial charge, divided by the number of parts that you make. Divided by the number of parts that you make. So, if each of this has a small charge q, this q will be that original charge divided by the number of parts. So, it will be q by 27. So, this is basically the new charge on each drop. So, this is nothing but the new charge on each drop. New charge on each drop. Okay, so this much is sorted. Now let's go to the next one. We have this, and I'll just put over here this small q is capital Q divided by 27. What is new potential to old potential, new capacitance to old capacitance? Okay, before going there, I have a feeling that the volume will be conserved. Why is it that the volume will be conserved? Because whatever the matter is there, it should not be destroyed. So I can just say volume is conserved. Volume is going to be conserved. So what is the initial volume versus what is the final volume? Initial volume is 4 by 3 pi r cube. The final volume is 4 by 3 pi small radius cube, but there are 27 such drops. So the total volume of 27 such drops is this big solid sphere's volume. Okay, 4 by 3 pi cancels. So we are left with r cube, and 27 is actually 3 cube. That's going to be useful. That is capital R cube. So therefore, capital R is nothing but 3 times of small r. I will use this maybe for solving the questions. How exactly? Observe now. Capital R. So if this is nothing but R, so this new radius is R by 3, or this radius is basically 3 times of small r, one and the same thing. How do I use this now? Observe. If I want to find new potential to the old potential, new potential to the old potential, new potential to the old potential ratio. What's the formula for the potential of a sphere? KQ by R square, sorry, KQ by R. Isn't that the formula? So Coulomb constant into basically the charge, which is nothing but Q, divided by R. Here, old potential will be K capital Q by capital R. K cancels, so we will have Q by capital Q and we'll have capital R by small r. You can replace anything with anything, like small q is capital Q by 27. This capital Q stays as it is. Capital R is 3 times of small r remains as it is. As one can see easily, R, Q cancels, this 3 cancels with 27, 9 times. So hence that ratio will be 1:9. So the new potential is to old potential. We figured out the ratio. It is nothing but 1:9. Everybody with me on this? Last part of this particular problem, where we have to find the capacitance. Capacitance of an isolated sphere is 4 pi epsilon naught R. So this was our old capacitance. The new capacitance is 4 pi epsilon R, small r. So therefore, just finding that new capacitance by old capacitance ratio, it will be small r by capital R. Capital R is 3 times of small r. As we can see, small r just got cancelled. So we are left with 1:3 ratio. So 1:3 ratio is the capacitance new is to capacitance old. That's it. Everything we figured out. So we had to use the concept of volume conservation. We also had to use the concept of charge conservation. So, each drop into the number of parts will be the total charge which was there initially. So it just got divided. So we found out each charge, how much was it. We also found out what is the new radius. And once we got the new radius, that's it. We can find potential using KQ by R formula, capacitance using 4 pi epsilon naught R formula. So this formula is the recently learned formula over here. Okay, 4 pi epsilon naught. So whatever we have learned today, what is capacitance, what is the unit of capacitance, what is the symbol, where does it store the charge, what is the force between the plates, what is the force on a third party charge, what's the different formulas for parallel plate, cylindrical, spherical, and a special case of isolated spherical capacitor. And if you've forgotten to like the video, like it. And if you've forgotten to smash the subscribe button, smash that subscribe button as well.